Well, as you recall, we started with defining integrals of functions on intervals, and then this semester we generalize it to regions in plane, and then to solids in space, that is definite integrals, double integrals, and triple integrals. Within our perception, we did not do this for curves and for surfaces. Namely, we did not define an integral where the domain is a curve. Well, we defined it when it was a line segment. That's definite integrals. And we did not define integrals over surfaces, which in particular, for instance, double integrals are defined on surfaces in xy plane, but that's a very special case. Okay? So these generalizations of integrals are possible. Well, this semester we will not be talking about integrals over surfaces, which are called surface integrals, but we will talk about integrals over curves. Somehow they are not called curve integrals, they are called line integrals, even though they will not be lines. That comes probably from a historical remark. Okay, so the setup is the following. Okay. Given a curve, say in plane, okay, which can be characterized as a graph of a function. Okay. We can find its arc length, which we defined it that way by okay, integral a to b square root of 1 plus f prime x squared dx. This was a formula we already knew. Well, what is this actually? This is the limit of Riemann sums, okay, where we have pi minus 1s in length and I running from 1 to n. It was basically this. Now, what are these pi's? Well, in plane, say this is our curve, C. Okay, we partitioned C into pieces. Okay, we started with some, say, P0, and then P1, etc. And then we had some Pk minus 1 and Pk, and we connected these points which was exactly the length of Pk minus 1. So, adding these terms, okay, these differences, okay, we obtain an approximation to the length of the curve, and when we pass through the limit, okay, we obtained the arc length. Now, it is important to see what this is. Well, this is actually the length of xk, yk minus xk minus 1, yk minus 1. So it is the square root of xk minus xk minus 1 squared, yk minus 1 squared. Now, if we call this delta x, so one approach could be that this is almost, okay, delta x squared plus delta y squared, which would be, okay, 1 plus delta y over delta x squared times delta x, okay? And this could be approximated by 1 plus the derivative squared delta x, which we did in our previous observations. Now, if the curve is, okay, given parametrically, what would happen? Well, we cannot talk about the derivative of y with respect to x anymore, but at this stage, okay, we would deviate from here. We would not do this, but we would do the following. If curve is, well, curve is C, if C is given parametrically, okay, then this term would be something like, okay, delta x over delta t squared plus delta y over delta t squared delta t. Or it would look like x prime t squared plus y prime t squared dt. Okay. So if parametrically given, we could use x primes and y primes and put this in our limit, in our Riemann sum limit, and obtain this. Of course, this would look like a little bit different, but it's the same type of calculation. Now, two things about this review of arc length. Firstly, if we had a curve in space, okay, the same argument could be repeated. So if C were a curve in space, okay, we could define arc length exactly the same way. Okay. Okay, let me say, can be defined, okay, exactly the same way. Namely, limit of the sum of the lengths of the line segments. Well, of course, when we open up the length of a vector difference in space, we would obtain three terms. Namely, this would look like then the square root of, okay, xk minus 1 squared, yk minus yk minus 1 squared, and zk minus 1 squared. And parametrically, this would give us the square root of x prime t squared, y prime t squared, z prime t squared, dt as before. So there's no big deal here. We just add one more component to calculate the arc length. Now, suppose we have the same type of integral, that is this limit. But somewhere here, we put a function. Okay. What would happen? Well, we could consider as well the following. Okay. We have a curve, a C curve. We have a partition, P1, P0, P1, etc. Some Pk minus 1 and Pk, and some Pn at the end. Okay. We form the same type of Riemann sum here, namely, we consider these lengths. Okay? And we define the limit of this sum of, now, this time, okay, we will choose a point between them, somewhere here. Okay? Call this sum P, say, I star, or rather, because I have K, Pk star. It's a point on the curve, but in the arc from Pk minus 1 up to Pk. It's an element of the arc. So, and of course, we have a function. We put the value inside the function and multiply it with Pk minus 1. And if this limit exists, okay. So what is happening? Well, we are, first of all, working on a curve all the time. Okay, we have a partitioning of the curve into sub-arcs, namely the arc, say, P0 to P1, P1 to P2, Pk minus 1 to Pk. Okay. Now, because we already had clear-cut and easily calculable way of measuring the length or the area or the volume, okay. Here we have arc length. That could be very cumbersome, so we just look at the length of the line segment, approximating the length of the arc, Pk minus 1 to Pk. Here, no, this is a Riemann sum. Okay. Only here, the measuring way is by looking at the line segment. So, if these Riemann sums have a limit, then we call it line integral. Okay. So, pre-definition. If the limit, of course, limit when pk's get closer and closer. So their lengths, the length of the difference goes to 0, as usual in a Riemann sum. So we have f of p, say, k star times length pk minus 1 exists. We call it line integral of f over c, okay, actually line integral of the first kind. And show it by integral over c of f. Well, since we want to apply f to pk star, which is a point on the curve, but actually it is a point in plane at the same time. So f must be a function of two variables. And we put here ds. Okay, this is arc length, or rather differential arc length. Which can be, okay, written from our previous arguments as the square root of x prime t squared, y prime t squared dt. So this is the differential arc length. This is the way of showing it, but actually instead of ds, we put the length of the line segments. Well, if this exists, we call it the line integral of the first kind of f over c. Well, first of all, the line integral over a curve is defined through Riemann sums. So the first thing we infer is that all the standard properties of Riemann sums should be valid. That's to say, okay, this is the limit of a sum, so line integrals must be linear. That is, integral of Cf plus g must be C times the integral of f plus integral of g, and so on. Okay. Well, the formal definition will require a little bit more work. Let me just state this. We will not be using it anyway, but it's good to know the definitions. Okay. Let f from R2 into R, okay, be defined on C, a curve, okay, in plane. Then, if there exists a number such that for all epsilon there is a delta, okay, we are talking about a limit, such that, okay, for all partitions P0, P1, Pn of C. Okay, so here C needs to have a finite length, as you can see from the definition, okay, and it must have endpoints, all right. Or the endpoints can be the same. It can be a closed curve, but still it has endpoints. So for all partitions of C, such that the maximum of these, when k runs from 1 to n, okay, is less than delta, and all pk stars in the arc pk minus 1 to pk, okay, one has the Riemann sum is less than epsilon, then I is called the line integral. Shown by this form. Well, as I said a minute ago, okay, the line integral is defined as a limit of Riemann sums, and therefore it should obey the standard properties. So, okay, since defined as limit of Riemann sums, one has the following properties. Okay. Well, assume that we have integral of fxy, ds is f, and gxy, ds is g, exists. Then integral c of any kf plus g ds would be kf plus g. That is, linearity holds. Okay. 2, if fxy is less than gxy for all points in C, one has integral of over C of f ds is less than integral of g ds. Well, we expect this because g minus f will be positive in this case because g is bigger than f. And if we look at the Riemann sums, all the Riemann sums will be positive for g minus f. And so, okay, the limit will be non-negative, actually usually positive, but could be 0, of course. And so the integrals will satisfy this. Okay, this was called monotonicity. And the third basic property, if C is, okay, two curves put together, okay, piecewisely, smooth, etc. We will not go into that at this point, okay. And, okay, all integrals exist, then one has integral C f ds is integral C1 f ds plus integral C2 f ds. That is decomposition. And finally, the geometry of the line integral. That's to say, integral over CL1 ds is the arc length of C. Actually, as we already talked about this, okay, without defining arc length, okay, as a term, we obtained a way to find it, okay. But actually, this is, if you look backwards, this is the definition. So if this line integral exists, it's called the arc length of C. So far, okay, we defined the line integral, but still we don't know if it exists or not. Well, as usual, we have the existence theorem. That is, if f is continuous and C is smooth enough, piecewise smooth, the integral exists. So, existence theorem. If f is continuous and C is piecewisely smooth, then integral CF ds exists. Well, this theorem actually does not change for any type of Riemann integral. Continuity is the most important property here. Well, of course, we require some smoothness properties depending on where we define it. We didn't need that in definite integrals because the interval is as smooth as you can ask for. Okay. So these being the properties, right. Okay, let us note that clearly this can be generalized to line integrals on curves which are space curves. So a remark. Okay, this can obviously be generalized to space curves. Okay, shown by this formulation. Well, so far so good. We have our ds, and we have our Riemann sums, so the theoretical properties are nice, but how do we calculate them? Okay, calculation can be done, okay, by parametrizing C. Okay, when we parameterize C, we know what ds is. Namely, ds was, remember, square root of x prime square plus y prime square plus z prime square dt. Okay, or the squares are under root, of course. Right. Well, the second question could be, why do we introduce line integrals? Well, well, this is certainly a concept, as many concepts of such integrals, multivariable integrals, they come from physical considerations. Okay, we will just explain one example here. Okay. Well, consider, okay, a wire, say, in the form of something, okay, and starting from this side, okay, the wire has a density. Well, but the density is not constant. It's a variable density. It's an alloy. Okay. It's made by combining different metals, but it was not done in a very uniform way. So some parts are heavier, some parts are lighter, and so on. With variable density, say rho x, actually rho xy, okay, at point xy in C. Question is, what is its total mass? Of course, this density is per length. Okay? At each point it changes, but it's a density per length, because C only has a length. As you can assume, its cross-section is constant. Doesn't matter for us. So then, what's the total mass? Of course, if you take your wire, okay, and divide it into pieces, in this piece, for example, okay, which is of length delta S, okay, the arc length, has almost constant density. Okay. But from this point to this point, when you move, okay, you are changing from a pk minus 1 up to pk. So the total mass is the limit of the masses that you can check here. This is rho xy times delta S. Okay. Namely, mass is per length. So the mass of this piece would be roughly density, which is almost constant, times the length. So okay, this would be the limit of rho xy delta S, which of course is C rho xy ds. So you can only find this total mass by using the line integral. But Okay, there is more to it. To be explained soon. So this is not the only application that you can get from line integrals. Okay, to do some calculations, okay, let us work on some examples. Okay, let us, to start with a simple example, let us find the length of the circumference of a circle of radius r. Actually, we did this, okay, using 1 plus f prime x squared and so on, using the fact that such a circumference, or at least part of it, is the graph of a function. And we used our previous knowledge, and using definite integrals, we calculated that. But now we want to use our new knowledge, that is parametrization. So, okay, parameterize, okay, C, that is the circle, okay, using anything you can use here. There are many choices, but let us use the standard cosine t, sine t version, t 0 to 2 pi. We already worked this out. But then, okay, the length becomes integral c of 1 ds. Well, that's the definition of length. This is, okay, even though this is a closed curve, we don't care about it because we have parameterized it. We are not talking about the graph of a function anymore, so you don't have to look at the top part only. So this would be integral of 1. Now ds was the square root of x prime t squared plus y prime t squared dt. And t, of course, changed from 0 to 2 pi. By the way, if it's a radius r in the parameterization, you need r's, of course, because the sum of the squares must be r squared. Well, what is x prime t? It's minus r sine t, squaring r squared sine squared. The other one, r cosine t, squaring r squared cosine squared. So this is actually r. So you integrate 0 to 2 pi r dt, which is 2 pi. So this parameterization simplifies greatly the calculation. We don't have to deal with square roots and other things, etc., etc. So it's quite trivial to check this up. Okay. Well, a second example is to calculate integral over c of x plus y squared ds, where, okay, c is the unit circle. You must have noticed, of course, that when we talk about the curve in this first type of integral, I don't care about the direction. Okay, because in the Riemann sum, I have the length of pk minus 1, which is always positive, whatever the direction. Okay, so we don't care about it. It doesn't come into the picture. But it will in the second types, which we will discuss after this. So, well, okay, you can directly put in, okay, actually, yes, that's good enough. So you can find some parametrization because it's a unit circle, something like cosine t sine t works, and t is from 0 to 2 pi. And so the integral, that is x plus y squared ds, okay, becomes integral of x times y plus y squared, okay, and ds. Well, ds was, remember, square root of the derivative squared, okay, and then dt. And t runs from 0 to 2 pi. Okay, now this term, of course, is 1 because you have here sine square, you have here cosine square, and you don't have anything else here. You can directly compute this. Well, computing this, because this is 1, you have cosine t 0 to 2 pi. Well, it's a full period, so the integral is 0, if you want. Antiderivative is sine t, and so 0 to 2 pi, you have 0. For sine square t, you have 0 to 2 pi, okay, 1 minus cosine 2t over 2 dt, which of course happens to be, maybe I should just put it here, that would be 1/2, okay, minus, well, an antiderivative would be sine 2t over 4, and you put 0 to 2 pi. Well, for the second one, you have 0, clearly, so the whole thing is pi, so this is the value. Now, what it represents, at this point, it doesn't represent any geometric meaning, okay, except that, well, as we said, for example, if x plus y squared is density, then you get total mass, but this is not a natural definition. Okay. As a third example, let us find integral c of xy okay, ds, where c is the line segment okay, from 0, 0 to 1. Okay, note that x and y, or the pair xy, is chosen on the curve. So let us formulate this curve first. Okay, it's from 0, 0 up to 1, 2. It's a line segment. Okay. So clearly y is 2x. So we can formulate it. say we have x and 2x, okay, and x changed from 0 to 1. This, of course, gives us all points on this line segment. But then the integral, okay, would be clearly the integral from 0 to 1, because x changed there. Note that I'm using the trivial parameterization. Okay, so this is the trivial parameterization, because this is the graph of the curve y is equal to 2x. So we have x is x, y is 2x, and ds is the sum of the derivative squares, dx. Okay, so it is 2 root 5, okay, and x cubed over 3, so 1/3, as direct computation shows. Well, as a fourth example, let us calculate the length of the arc, okay, of the curve x to the 2/3, y to the 2/3 is 4, from 3 to the power 3/2 and 1 to 8, 0 in the first quadrant. Well, we can do this as we did before, namely using a definite integral where we use square root of 1 plus f prime x squared. So the first method could be, okay, use trivial parameterization. Okay, this leads to, okay, integral of root 1 plus f prime x squared dx, okay, as before. That is, as we found it in 119. Okay. So we will not do that. We will try a different way, namely, okay, choose a different, okay, but a more appropriate parameterization. Well, what do I mean by that? Actually, you have infinitely many choices. I mean, parameterizing a curve is not a clear-cut, well-defined process. You can find infinitely many representative functions for the same curve. Okay. If you look at the equation of the curve, you see the following. We have cube root of x squared plus cube root of y squared is equal to 4. This, in some sense, resembles, okay, a circle. It's not a circle, of course, but it's the sum of squares of x's and y's, which is almost like a circle. Well, if you want to generalize such a process, you can consider, okay, these arguments. Okay, a circle, okay, say of radius 1. Here the radius is 2, but it's more or less similar. Okay, this is obviously x squared plus y squared is 1. So consider x to the p plus y to the p is 1. Okay. But, of course, you have a square somewhere. Now, let me see to it that you have, that you have the squares. So you have, okay, let me put here 2 p's. So if p is 1, we get a circle. Obviously enough. If p is bigger than 1, okay, what do we have? If p is bigger than 1, since x and y are smaller than 1, okay, their pth powers are much smaller. Okay? So you have to put larger values of x and y to guarantee this equality. So what I mean is the following. Okay, if p is 1, you just square x's and y's, and it gives you 1. If p is greater than 1, you are squaring, okay, larger powers of x and y. Because they are less than 1, they get even smaller. So you have to choose your x's and y's from the beginning larger than those on the circle. So, because these 4 points are fixed anyway, okay, you get something like this. This is when p is greater than 1. Okay. Well, okay. Now, if p is less than 1, well, think of taking something like square root, because the power is less than 1. Well, if you take square root of a number less than 1, it becomes bigger. Okay? So, from the start, to satisfy this equation, you need to take them even smaller. So, it looks like this. This is if p is smaller than 1. Actually, if it's smaller than 1/2. Okay. Well, when p is exactly 1/2, clearly, you take the square root, and then you square it. So you take absolute value. Okay. Let me just put this as a last picture. This is just practical knowledge, so we will not be using it in detail. Okay, so this square is when p is 1/2. Okay. So all of them look like a circle, but they are not circles all the time. But in our parametrization, we can get the hint from here. So put, okay, cube root of x, say cosine t, and put cube root of y, sine t. Of course, in this case, the sum of the squares will be 1. Well, we want it to be 4. So put 2's here. If you square this and this, okay, actually what I mean is this, of course. Is that true? No. You have to put it here. Right. So when you square these things and add them, clearly you get the squares added. It will give you 4. So this is a parametrization. In other words, okay, you put x to be the cube 8 cosine cube t, and y 8 sine cube of t. This is similar to polar parametrization, but because of cube roots, you have you had to take the cube of them. And of course, similar to a circle, t runs from 0 to 2. Because t is the angle, and it makes a complete cycle. Now, with this parametrization, okay, let us calculate the sum of the derivatives squared. This, of course, would be a large square root. You would have 24 cosine square t and minus sine t. This will be squared plus the other one taken derivative and squared. That would be 24 sine square t times cosine t squared. Okay. Well, you can see from here directly that you have 24 squared under root. You can take that out. Okay. You have here, okay, cosine square on that is, yes, you have cosine square and you have sine square in both cases. So take one cosine square, you have the square root, so it's absolute cosine t, absolute sine t. They will get inside as squares. So you have the square root of, we took 24 out, we took sine square out, so you have cosine square t. Actually, what did we take out? We took cosine square as sine square, it's cosine square t. Here you take cosine square and one sine square, so it is sine square t, so it is 1. So this is nothing but 24 sine t cosine t. Okay. Well, why did I take the absolute value out? Because in the interval given, these are positive. So in the interval given, the angle is between 0 and pi over 2. Okay. Which means that sine t, cosine t are positive. Okay. So finally now, the length would be 0 to 2 pi, 24 sine t cosine t dt. No, t runs from, sorry, we have to take that out. This is not correct. Something is missing. What is that? Of course, this is not true. Okay. So we go from the point 80. Okay, we have this. This is 80. Okay. And we go up to the point 3 halves and 1 for 1. Actually, it's somewhere here. Okay. Right. So here, clearly, t is 0. But at the upper edge, okay, t is, we can find t at the upper edge. That is, y is 0. Sorry, y is 1. So sine t is 2. So that means t is pi over 6. So here, let me correct that. At 3 halves, 1, okay, y is 1. So where remember, y was 8 sine cube t. This is 1. So sine t is 1/2, and t is pi over 6. Okay, so we have 12 sine 2t. Well, integral would be cosine 2t with a minus sign divided by 2, okay, and 0 to pi over 6. Okay. This would give us 6, and at 0 you have 1. At pi over 6 you have 1/2, and this gives you 3 at the end. So this is just to show you that we can calculate arc length using different parametrizations. Maybe one is better than the other. Okay.